Okay, I think most people are ready to start, and it's it's actually 7 o'clock Lamont time. We have our Lamont time is a little bit later than real time. I'd like to welcome everybody to, on behalf of Lamont-Doherty Earth Observatory, to tonight's lecture, which is titled Earth's Big Ice, Ancient, Mysterious, and Changing. So I want to introduce myself. I'm Steve Goldstein. I'm the interim director of the observatory, and I'm a professor in the Department of Earth and Environmental Sciences at Columbia. Our public lecture series is really proud to showcase distinguished Lamont research leaders who explore our planet, discover how it works, identify critical issues, and highlight the broader implications for both society at large and our local communities. And we are committed to sharing our scientific insights as we believe that they're essential in shaping meaningful, actionable solutions to the challenges that we have in our world today. So tonight it gives me great pleasure to introduce Professor Robin Bell, who's standing here. Professor Bell is the Palisades Geophysical Institute Lamont Research Professor within our Marine and Polar Geophysics Division. She received her undergraduate degree in geology from Middlebury College and her PhD in geophysics right here at Columbia. And what I want to do is I want to give you some insight about who you'll be hearing from tonight. Okay? Professor Bell is an expert on the structure of polar ice sheets. She has developed instrumentation where she images the inner workings and the landscapes that exist below the ice. She's led multiple aircraft-based geophysical expeditions to Antarctica and Greenland, studying what makes ice sheets work, how they work, and what makes them collapse. Among the many highlights of her career, her team has discovered several large lakes locked beneath the Great Antarctic Ice Sheet, and they discovered that water beneath the ice sheet actually runs uphill. She's discovered a volcano beneath the West Antarctic Ice Sheet, and there's actually a mountain in East Antarctica that's named in her honor. It's called Bell Buttress. Okay, so in recognition of her scientific contributions, Robin was elected a fellow of the American Geophysical Union in 2011, and the American Geophysical Union is the main scientific society for the geosciences in the world, and she's actually served as the president of the organization between 2019 and to 2020. Robin played a major role in organizing the last International Polar Year, and she is the first woman to chair the National Academy of Sciences Polar Research Board. Sorry, Robin. All right. Outside of her awesome scientific achievements, Robin is a passionate sailor who, alongside her husband, Carl Copland, recently, and when I say recently, it's this past May, completed a circumnavigation of the Earth in their sailboat. So there you have it. I hope you're psyched. I'm psyched. So at the end of the presentation, there will be opportunities for questions. So please hold the questions. And without further ado, Please join me in welcoming Robin to the podium.
So let's see, can you hear me? Okay, that's always, and thank you, Steve, very much for that introduction. And thank you all very much for coming tonight. And we're so happy it didn't snow as much as we like snow and ice. I hope today to give you you'll walk away with a little bit better understanding of our planet's big ice and how it's ancient, mysterious, and changing. And I am just the storyteller here. You know, science is produced by teams and mostly federally funded, and I'm really just the one telling the story. So I always like to start off by thanking all the amazing people, some of whom I see hiding in the audience, who've helped make these stories come true. So just remember, we have this sense that science is like, you know, one hero or person, not, okay? So my humble thanks to everybody who's helped me with this and helped us learn about the planet. So I would just like to start with a little bit of history. And some people here actually played here as kids. And Marie Tharp, who made this beautiful map, has this wonderful, what? Can you, I can't turn it up. It's not working? This is on, I can move it closer. See if that helps. Does that help? We'll try. Marie Tharp made this beautiful map and has this wonderful quote. It was very exciting in those days because things were beautiful. I think things are still exciting, and studying our planet is still one of the best jobs in the world. Oops, I just turned things off. So we're going to take a trip through the ice. I call this big ice. This is what it looks like when you're standing on top of big ice. But it turns out that we are surrounded by the fingerprint of big ice. This is a picture of big ice in Central Park. You can see this skyline in the background. And those are where I like to think of it as ski tracks or skiing into the woods. It's where the glaciers pretty much left their marks right here in Manhattan. Or I like to think of, if you were to look back into Rockland County and you see all these beautiful little hills. Isn't that a gorgeous fabric? That is left from the ice sheet. We are surrounded by the fingerprints. We live in a big ice-shaped landscape. It's one of the things I learned sailing around the world, is that landscapes molded by big ice are ones that say home to me. You know, I grew up in New England, so these are my kind of landscapes, kind of not those pikey mountains, but those big smooth ones, just like what we have here in Rockland. So those of us who live in Rockland or even Northern Bergen, you live in a big ice landscape. And this is what it used to look like, you know, just 20,000 years ago. See the big blue blob up over North America. Greenland's still there. There was a big blue blob of ice over Europe too. And so right now we're sitting right here on top of the Palisades, Hudson River running north and south. It's about an hour and a half drive to the beach. But when big ice was here, it had named Laurentide and Fennoscandia, there was a lot of water stored in the ice. And the oceans were a lot further away. As I like to think of it, the ice would have been right over us, probably about a mile thick. And it would have been about a 4-hour drive to the beach if we could drive. See, the beach would have been way out here. Sea level would have been that much further away, the beach, because all the water that used to be in the ocean is sitting on top of us here in the auditorium. But what's fascinating, and I've really listened for a long time, is who heard those stories? Who in humankind heard those stories of what happened from when it was a 4-hour drive to the beach to when it became an hour and a half? And we stopped in Australia. And one thing I learned in Australia was the impact of sea level on humanity there. When sea level was lower, you could walk from Papua New Guinea to Australia. So that's when the first people arrived in Australia. These are the dates. It was all about 45, 46,000 years ago. People arrived by walking. They hopped little bits of boats here, but they walked from Papua New Guinea to Australia. And they even walked all the way down to Tasmania by 40,000 years ago. What does that mean? It means that there are people who were there when what we think of as the Great Barrier Reef, what it looks like today, a modern Australian beach. The people, the many, many mobs of Australia, that's the groups of the indigenous people, the people who arrived, they watched the landscape. This is what the Great Barrier Reef used to look like. It used to look like grasslands. Can you imagine that? And if you listen to the stories, and we had the honor of, because you travel slow by boat, you have a chance to talk to more people, learn some of these stories from different people as we traveled up and down the coast. And then there's a very nice piece of work by Patrick Nunn, who captured the stories of how the beaches changed, how sea level rose. And they started with stories of blame. You know, whose fault is it? They started to stories of places that became islands and efforts to stop them. So, as you could imagine, if you were used to those beautiful grasslands, what happened when suddenly they started to become a beach? Your life was changed. So the blame, you can hear it all around Australia. If you listen to the stories, you can hear stories of someone who killed a fish, and that's what was causing sea level to rise. Your ancestors were bad. They happened to have blue-tongued lizards. They were causing the sea level to rise. Evil kangaroos, a hurricane, or, I love this one, on the south central Australia, the narrative is that it was because trees were cut down. That was because they knew that the trees absorbed water, and they assumed that somebody who cut down all the trees were making the water go back into the ocean. So that was the blame. There were stories of peninsulas becoming islands, you know, stories where the rising water were isolating communities, and the very famous Tiwi community north of Darwin. And it's a story of a woman walking around, and she's the one that molded the landscape as the sea level rise happened. And what's remarkable is there are even stories of actions they took to try and slow it, because they, like us, are trying to understand how it all fit together. There are people who there are stories of putting up trees to try and stop the sea level rise, or of walking to the edge of the Great Barrier Reef and throwing hot stones into the ocean in hopes it would evaporate. So it's fascinating. Sea level's rising again now. This time it's because of ocean warming and changing ice. So let's take a tour. Now that we've kind of gotten a sense, we live in a big ice landscape. Humans have watched sea level rise in the past, but that was the natural oscillation depending on how much solar energy is coming into the planet. But now it's going up. Everywhere there's a little arrow going up, this is a nice NOAA site. You can go click on it anywhere you want, and you can see the record of sea level going up. You can see a couple places are going down. That's because of it's still bouncing back from the last big ice. But we can measure it. These are two places in Australia. You can either measure it by making a carving on a rock and coming back 100 years later and seeing whether or not sea level is at the same place, or you can do it by putting an instrument down in the water and watching it. And there's one down in at the Staten Island Ferry. And as I like to say, it's been there since before my grandmother was born. So my grandmother was born about here. And you can see, you can see some variation, but in general, the sea levels going up very consistently. And as I like to say, sometimes we look at these graphs, they don't, particularly this one's in centimeters. We don't think in centimeters. But if you put your hand on your leg somewhere just below your knee, that's how much it's risen since my grandmother was born, right here in New York. So we have sea level is changing. It's a pretty clear signal. And in those signals around the world of all those arrows going up, we're starting to see the signature of big ice changing. So what is big ice? Big ice are those big pieces of ice still left on our planet, the ones that, that not like the Laurentide and the Fennoscandia, the ones that were in North America and Europe. So there's Greenland, in the news a lot today. And there's two in Antarctica. They're very different. They have very different characters. So we'll talk about them differently. There's West Antarctica, surprisingly in the Western Hemisphere. And there's East Antarctica, mostly in the Eastern Hemisphere. And if you think in terms of states, here's Texas for scale, or this piece is about the size of France. So they're big. It's the ice in Antarctica is big. If it all melted, it would, in West Antarctica, about 19 feet would rise globally. Greenland, about 20 feet, 24 feet. And East Antarctica has the most, 170 feet. So there's a lot of ice still left on our planet. That's water that's not in the ocean. So we're going to take a tour. We're going to start with my favorite ice sheet. I don't know. I'm not sure if I have a favorite ice sheet, but we're going to start with the one that I'm most excited about right now, which is East Antarctica. So it's also the oldest ice sheet. And this is now we're looking at a very long time scale. We've been talking tens of thousands of years. That's how, 20,000 years was when the ice was last here. 40,000 is when humans arrived in Australia. But to go back to an ice-free Antarctica, you actually have to go back 34 million years ago. The Earth's climate was warmer. This is temperature here as we get it. You can see there's, in the last 50 million years, there's been a general getting colder. And you can see at the same time, the CO2 has been getting lower. You can see why we're worried about CO2. And you can see there are different phases. First, you could walk around everywhere. You can go hiking in the center of Antarctica. There were, Northophagus trees like you find in New Zealand. And then as CO2 dropped and temperature began to drop, you grew an ice sheet in East Antarctica. So that happened about 34 million years ago. The things we're going to look at in East Antarctica have been covered probably for 34 million years. Then we're going to look at West Antarctica that grew sometime around 12 million years ago. And then we're in this period where we were oscillating between big ice sheets and little ice sheets, and big ice sheets and little ice sheets as things got very cold. And this is where we started to grow ice in the Northern Hemisphere, the ones that we live on the fingerprints of. So that's how we know how old the ice sheets are. But what I'm going to do is take you in a tour underneath. This is what it looks like on top. They flow away from the middle, but we're going to look at the terrains underneath. I was the kind of kid who went in the backyard and picked up all the rocks to look underneath. So this is kind of my job, is pick up the rocks, the ice, and look underneath. So we're going to look at a couple of features. You can see blue shows that West Antarctica's below sea level. This would be an open ocean if there was an ice sheet here. East Antarctica, much of it is, I like to think of it as Canada, cold old continent, sitting up pretty high. So let's go take a cross section of these. So these are these long lines, just give you a sense of how much ice there is. We're going to look at Dome A, where the ice is the highest, about 4,200 meters. And we're going to look at the Gamburtsev Mountains. We're going to look at Lake Vostok underneath. And then we're going to look at West Antarctica. So these are, if you were looking at a cross section. And some of these are more susceptible to change than others. Ice sheets are susceptible to change either when they're closer to the equator, like the one that isn't here anymore. It was susceptible because it was close to the equator. Greenland's further south or closer to the equator than these, so it's more susceptible. Or if you have it in an ocean, because then it can be warmed by the ocean. So let's look. How do we look through the ice? We look through the ice a couple different ways. And originally in the IGY, when the very early people who worked in the poles, like Ken Hunkins and Charlie Bentley, they drove around in the IGY, they set off dynamite and measured gravity in between the dynamite, and they listened to the echo. And that's how they figured out one of the big findings during the IGY, 1958, was that there was way more ice than they thought. They thought the ice was just a thin skin. They didn't realize that it was miles thick. So that was one of the big discoveries. It's pretty slow to drive around and shoot off dynamite. It's way faster to fly over ice sheets. So that's what we do. We put instruments. If you come to our open house, you've been able to see the ice pod, which snaps onto the outside of a C-130 or Twin Otter, where we bounce energy, radar energy, through the ice sheet and listen for the echo to come back. That's how we measure how thick the ice is. And that's let us understand the terrains underneath. So this is, again, what one of our research aircraft looks like, the Twin Otter. The antennas sit on the wings, so we send the energy out. We fill the inside with lots of other instruments. But this is what our data looks like. So this is the layering in the ice. This is about 20 kilometers across. And so you can see mountains underneath, right? Jagged mountains. But the other wonderful thing we often see, particularly in West Antarctica, is we see very bright reflectors at the bottom. And that's water at the bottom of the ice sheet, which one of these things that makes you scratch your head, because the average temperature here is -50 at the surface, or -40. -40 is easy because it's the same in Celsius and Fahrenheit. So we're going to go in, we're going to look at this big piece of water, I think, next, Lake Vostok, which you can see is beneath 4 kilometers or 2 miles of ice. It was discovered when we first were able to make images of the ice sheet surface, because it kind of stands out, right? You see this little lima bean thing? Everything else is kind of rough. And so the Russians, it turns out there's a Russian base right on the top of it, because during the IGY, the Americans managed to secure the geographic pole. And at that point, the magnetic pole was roughly there. So they put a station on top of what turned out to be Lake Vostok. They didn't know it was a lake then. How do we know it's a lake? This is that when you look at the ice surface, you see this big flat space. How big is it? That's New Jersey. And how flat is it? It's flatter than the runway at Newark Airport. That's pretty cool. So why is it? It's flat. It's pretty much because the ice is floating. You know, if you've ever gone out on a lake and the ice is really flat there, you can ski, it's beautiful. But if you're up on a glacier, or if you're coming down a hill, that snow and ice is hugging the terrain. So that's the difference. Over a lake, the ice is floating, but over much Antarctica, it's hugging the terrain. So that's how, when we look at this, we know that this has to be floating, and the rest of this has to be stuck to the ground. And one of my favorite ridiculous moments in science was standing at a poster with a bunch of people, and they were all looking at this and saying, wow, look at Lake Vostok. And I'm like, wait a minute, guys, what are those? Aren't those lakes too? It was one of those most fun things to be able to stand with a bunch of people and look at data that they, was off to the side, and realize you could discover something. Oops. Just standing there. Is it still working? I think I knocked it. Okay, good, thanks. So this is just a cross section, and coming back to the question of, wait a minute, why, if it's -50 at the top or -40, is there water at the bottom? Well, it turns out that even there's geothermal heat coming up from the bottom and warming the base of the ice sheet. It could also be friction. When the ice starts moving fast enough, it melts at the base, but this ice is only moving about 1 meter a year. Has to move 100 meters a year before it really melts at the base. So this is just geothermal heat coming up and warming the base of the ice sheet. And it happens that there's a big basin here, probably geologically formed, where the water accumulates. And one of the interesting things is it turns out that we could tell that ice is freezing, water is freezing back onto the base of the ice sheet. That was one of the fun things we discovered when we flew a survey over this lake. So that's Lake Vostok. Water's there because the ice sheet can only get so thick before it melts at the bottom. During the International Polar Year, one of the real goals was to go back to the top of the ice sheet, Dome it's called, and underneath is the Gamburtsev Mountains. Nobody had really systematically surveyed them since they were discovered in 1958 during the IGY. And it just seemed to be one of those places that was very hard to get to. But an International Polar Year was the perfect time to do it, where you could get 7 nations to work together. So we got 7 nations to work together. This is Lake Vostok you were looking at before. Those are those 2 little lakes. This is South Pole. And this is the top of the ice sheet. And these are all the lines we end up flying. But this is how many countries it took to get there. It really took 7 nations, several years of planning, and a lot of persistence to get there. But what we found was amazing. I used to carry around this picture in my wallet, and I'd show it to anybody I met. You know, I'd go to a parent-teacher conference. I'm supposed to be talking about my kids. It's like, you want to see this cool mountain range? Or I'd go to a doc and be sick and be going to see a doctor, and I go, you want to see this cool mountain range? Anyway, it is an amazing mountain range because it, you write things in proposals saying we're going to find this, we're going to find this, but then you see it, and oh my goodness, it looked like river valleys, which I don't know what we were thinking. Of course, there's going to be river valleys, but it was just so spectacular. This is the contours it's showing. This is the tippy top part of the ice sheet on that transparent layer, and underneath are the beautiful rugged mountains of the Gambertzes. That nobody's ever walked on, and nobody will in our lifetime, not for probably millions of years, because they have been covered for 34. So that's what it looks like when you look down on them. The head of the dome is right here. But what we also wrote, we'll find water, because you always have to put out hypothesis and go, oh, well, we'll study the lakes we're going to find. I really didn't think we were going to find lakes. It's like, oh, sure, find lakes. Turns out every single one of these valleys had water in it. Totally a surprise for us. And we also started to understand how old the ice was. It was the bottom of the green is 120,000 years. So the ice is really old. There's probably million-year-old ice there. But the other thing we saw was this really weird thing that's called yellow here. It's called freeze-on. But let's look at why we think it's freeze-on. Most ice sheets have beautiful layers, right? Snow falls, it collects as a nice horizontal layer. That's what it's supposed to look like. We kept on seeing these things that were not. And then you're supposed to find mountains underneath, right? We were studying the mountains. We were expecting to see raggedy things. But there were these things that didn't look like mountains and didn't look like layers, but were really persistent. And of course, being good scientists, we assumed it was something wrong with our instruments. But then it kept on showing up on line after line after line. And we kept on collecting our data, because remember, it was really hard to get there. So when we get home, we mapped them out. So here are the same river valleys, right? And the top of the ice sheet. And oh my gosh, they were on both sides of the mountain range. And the nice thing with this was flown by the British, so it wasn't the instruments, right? Because if the British flew it with one instrument and saw it, and we flew it with a different instrument and saw it, unlikely to be a problem with the instrumentation. But they all seem to be coming out of the heads of the valleys. And see how you go up the valley like this, and there's one of these coming out. It's almost like something's flowing out of the end of all the river valleys. So our hypothesis, and what we still stands today, is that because every single valley has water in it, and normally we just think water runs downhill, right? But when you put an ice sheet on it, you can squeeze that water uphill. So what we found was that the water was being driven uphill and refreezing when it got to the cirque, where you would go skiing, right? Where there would be a beautiful ski area, a parking area, and you come down that cirque. But instead, the water's going uphill, and when the ice sheet gets thinner, it freezes back on again and again and again. So this is, so it was like this double lines of evidence. One is the geometry says the water should be running uphill, but we also have these structures that we can track that go on for tens and tens of kilometers that show that the ice sheet's thickening from the bottom. We went on to find similar ones in Greenland that we're just starting to be able to see that these are probably about 60,000 years old. We're just starting to look at the ones in Greenland, and they're probably hundreds of years old, much, much younger. So those are my favorite places in East Antarctica. I'm going to take you to one place in West Antarctica. And sorry, if I'd known they were going to talk about volcanoes, I'd show you pictures of volcanoes, but I didn't. So I'll just have to tell you, there's a volcano in the middle. It's active. You can tell because the ice sheet sags over it, and there's no way to make a great big hole in the ice sheet unless you're melting it from the bottom, so it has to be warm. So this is the Ross Ice Shelf, big piece of floating ice the size of France. And this is the very susceptible West Antarctic ice sheet, below sea level. The geometry means it's the warm water can make it unstable. If it melts at this place, it goes afloat. The ice isn't anywhere near as old. The radar's not anywhere near as beautiful. You can see this is the bottom of the ice sheet, kind of boring, because it's an ocean, right? It's not a mountain range. But the ice is like 60,000 years, barely older than people in Australia. But there are lakes there. They're not as beautiful as Lake Vostok, but the difference is you can see the water moving from one to the other. This is work done by a friend of mine, Helen Fricker, who found that she could see areas on the surface of the ice sheet where one area would drop up to 7 to 10 meters and another area would pop up. And the only thing that could be would be a series of lakes where you could see water moving from one to the next to the next. Basically a cascading series of lakes. They have drilled into these, and yes, there is water. Remember, Lake Vostok is a half a mile deep. I think of these more as swamps. They're kind of a couple meters deep, not anywhere near. You could go canoeing in these, but not sailing really. Anyway, so this is the kind of terrains that are underneath the ice sheet that we don't think about. We don't think about there being big lakes, water systems that run uphill, and these water systems where the water goes downhill. Is the ice changing now? The evidence is, when I published the paper on the volcano in West Antarctica in 1991, we had to remove the lines about the ice sheet changing quickly. Because in the 1990s, we did not believe that ice sheets could change rapidly. It really has been the advent of the comprehensive satellite data that show very clearly that the ice sheets are changing. And I'm going to show you the evidence, and I'm going to show you 3 different lines of evidence. And scientists like to have more than one measurement. So I'm going to show you evidence for them speeding up. That's one measurement. I'm going to show you evidence for them getting lower. That's the second measurement. And I'm going to show you evidence for them losing mass. So 3 independent measurements of change. And we're going to start by looking at West Antarctica because that's where the change is the most dramatic. We're going to zoom in and look at a place called Pine Island. And between the 1990s, you can see it was moving, 1 to 2 kilometers a year. Sorry to be changing units on you, but then you can see by the 2000s, it had doubled in speed. It was moving twice as fast. Ice is kind of like mozzarella cheese on your pizza. When you pull it, it stretches and gets thinner. So as that speed up happened, you can see the ice sheet getting lower. This is a different measurement. This is made with a laser shooting at the surface of the ice sheet. The other one was made by tracking cracks in the ice sheet. So 2 different measurements showing us 2 different indications of losing mass. And then the third, this is actually where we're going to look at, this is where we were just looking. So we're going to look at from early 2000s to 2020, and red is loss. And you can see in the same place we saw it losing elevation and speeding up, you can see this pair of satellites in space that's measuring how much things weigh. You can see mass loss right here in the same place. You can see some in East Antarctica too, but not as large as in West Antarctica. There was a gap there. We didn't have satellites for a couple of years. And you can see there are places where Antarctica is gaining mass. Over here, there's been more snow. And right here, one of the great big, we call them ice streams. It's kind of glaciers that drain the ice sheet. This is stopped. So that's actually, it's gaining mass. It's like a conveyor belt that's stopped. But this gaining mass does not at all meet or balance out how much of the ice sheet is losing mass. So very clear signal in Antarctica, particularly in this part that's below sea level that we think is most vulnerable to change. This is less so in East Antarctica, and this part sits up pretty high, so isolated from the ocean. Just because I promised to talk about all bits of big ice remaining on the Earth, we're going to leap up and look at where Maria pointed to the north. to Greenland. It's about 2 million years old. The evidence, there's lots of evidence in Greenland, but one of the ones that, like you could take John McCain to or Hillary Clinton and they could go, oh, I can see change. All I have to do is take somebody up this valley and you see this dark and then this light line. The light line is where the ice sheet used to be. This is like weathered rock. It has like lichen on it and this kind of stuff you see around here. This light stuff, it's called the trim line. This is where the ice sheet used to be. So you can go around Greenland and see places the ice sheet has lowered, where it was until recently. One of those very visual, compelling pieces of evidence of the ice sheet changing. But we also have the same measurements. We're going to look at together Greenland over here, and you're going to see this is the mass loss. And remember, we saw this grow when we were looking just Antarctica. And if you look over on the left at Greenland, you're going to see that the mass loss is happening pretty pervasively in Greenland. And remember that Greenland sits further south than Antarctica does, so it's more susceptible to both the warming air that comes across our continent and then goes over Greenland, and also to the warming ocean, because its edges are touching the ocean, particularly the big outlet glaciers here and here. So you can see the signal is pretty coherent. And we've always thought that there's a seesaw and that, in the natural cycle, one ice sheet would go first and then the other. What we're seeing is these are both going pretty much at the same time, which is one of the lines of evidence for this has human hands on it. So what can we do? Human hands are behind these changes, and human actions are probably going to be necessary to keep the planet habitable for everybody. I like to say actions are needed everywhere, individuals, organizations, and governments where we can, local, state, and maybe someday again, the national government. But again, I like to show people the data and get them to reflect. By now, we feel, smell, and taste change. We feel on our lungs. We can feel the smoke from the wildfires. We can smell. In my garden, my daffodils are coming up earlier and my basil's lasting longer. And we can taste it both because we have basil on our pizza longer. And I'll show you that actually we're catching different fish in different places. So here's the data. Increase in wildflowers from 1990 to 2020. This is from the National Climate Assessment. Pretty clear upward trend. More fires, more smoke. Why are we seeing our plants come up earlier and our tomatoes last longer? And it's because since 1890, you can see this upward trend in the length of the growing season. So from here to here is 15 days. This is average for North America. There are some places in North America that it's actually 40 days longer growing season. So that's why the daffodils are coming up sooner, because it's warmer. And then, this is one of these crazy ones. This is latitude, where you're going to catch fish. This is in case you happen to like fish or are a fisherman. The fish, where we're catching fish, is moving north. This is again from the National Climate Science Assessment. Over from 1970 to 2010, you can actually see where you're catching black sea bass is moving north. The American lobsters are moving north. That's why the lobster fishery in Long Island is collapsing, and in Massachusetts, and why it's booming in Maine. Probably it's not going to stay that way. It's probably going to collapse there too. Cod don't seem to be moving. So just, in the honesty of a scientist, showing all the data that not everybody's moving, but change is happening. So we really are surrounded by change. We don't understand everything. If you were to ask me exactly how much sea level is going to go up, say down in Manhattan, there is still tremendous spread in our projections. And what we're learning is we actually have to think about how to make very localized projections and work with communities on how they connect with the environment and how they're going to see change in the future. So there's still a lot of work to be done. As reflecting on where we are, Australia's first people reacted to change by blame and solutions. I worry that we've been focusing way too much on blame, whether it's the oil companies, because blame and demonizing makes change difficult. I think we need to look how to build the knowledge necessary to support a habitable planet that's supported by evidence and rigorous science. Our planet's beautiful and it will be resilient. The question is, will we be as humans? I think we'll be. Our footprints on this planet are big, but it's really our responsibility to build a thriving, equitable, sustainable future for everybody. So what does that mean? There are all sorts of different things you do. In my family, it's actually why we sailed around the world, because my husband, here is Carl Copeland, is very serious about taking individual action. And it was our way to see the world together, because he's very committed to not burning more than his share of carbon. So, you can take individual actions, or you can, make sure you have a community solar. There are any numbers of things you can do. This is, I will admit this one's extreme, but it was a joy and I love it. You can also organizationally, you can make sure your organization is using renewables. Lamont's really worked to see if we can get solar farms to support our energy. Or even the organization you heard Steve speak of, the American Geophysical Union. This is our building in Washington. We renovated it and made it the first net zero renovated building in Washington, D.C. through using solar panels and green walls and heat exchange with the sewer system. What I learned from this is there's no single solution, that we have to look at multiple solutions. To get this to net zero, we had to do multiple things. We couldn't just put solar panels on top. We couldn't just build a green wall and put in LED lights. And we couldn't just do a heat exchange with a sewer. We had to look at multiple solutions. It's where we are. We need to look at multiple lines of solutions. So in conclusion, our footprints are large. We can smell, feel, and taste the change. And, I'm glad you came tonight, because it's a challenging time for all of us. And I have to say, especially for science and science institutions, and particularly for Lamont, which has a long record of understanding the Earth's climate. And we've worked really hard to shift the climate of geoscience so everyone can thrive. So, moving forward, it's going to be really essential to support people and institutions as they come under scrutiny. And, Steve can tell you, we already are under scrutiny. So thank you very much. And I really appreciate you coming and spending the evening with us. Okay, I think we have time for a couple questions, and I think there's a mic in both aisle if anybody has a question.
That was fascinating. How big a boat do I need?
Depends on what your tolerance is and what. Our boat was 38 feet, 22,000 pounds, 40 years old, and she got us around safely.
Thank you, Robin. In the beginning, you put up a chart from NOAA that showed the all the rises in temperature.
Mm-hmm.
Is that chart still up?
The only one I checked at NOAA was the sea level. Those are still up.
Okay. And can you speak a little bit about what will happen if
Oh.
your research isn't funded?
Oh, we're all terrified. We are we're primarily funded by federal funds here. The idea that they're cutting back overhead that keeps the lights on here. When we write a grant, it covers the salaries directly, but it doesn't cover keeping the driveway plowed and the lights on and the heat on. So overhead's very worrisome. We've already gotten, particularly in some of our diversity space, we've got stop work orders. So it's quite a frightening time to be a scientist. And we are hopeful that, institutions like this will weather the storm.
Hi, how much of the subterranean H2O that's in liquid form under extremely cold conditions is the function of increased pressure?
Not, I used to think that was what it was, but it's not. It's actually you only shift the melting temperature by about under those conditions by about 2 degrees. The bigger, and remember you start at either minus 40 or minus 50 at the top. So to get to close to zero, the 2 degrees from the changing pressure isn't going to be as important as the heat coming up, or either from the below or from the frictional heating. Yeah, no, I for a long time thought that that was it, but you hear?
Some names are Russian names. Some like something else in Russian. But they named them, or is it like the decision amongst the other?
No, it was, if you were to look at who drove where in the International Polar Year, the Russians drove all over, much more over East Antarctica. And there was, or at least that part of East Antarctica. Yeah, they named their stations, and you can propose putting names on things. There's here and here. Well, it's coming. I think that one.
What is your view about the risk to the AMOC from the melt from Greenland?
The risk to what?
The AMOC, the overturning ocean current that cycles heat around the world?
Well, it is, it is one of the things scientists are watching. It is possible to change it.
Thanks. That was a great talk. I noticed that the mountains that were surveyed under the ice sheet were quite jagged and sharp. And I guess I always thought about glaciated mountains as being sort of more rounded. So is that because is the ice sheet not moving, or why does it look like that?
That surprised us too, right? We were expecting it to look like New England, right? Or maybe the Adirondacks. They look much more like, they look like a younger mountain range. And our hypothesis is that it went from being mountain glaciers to being an ice sheet pretty fast. An ice sheet doesn't move very fast in the middle, right? It's moving 1 meter there now, whereas the ice that was here was probably moving 100 meters a year. So ice that's moving has more power to change than ice that's not. So that's what we think. And nobody's sampled it, so we really don't know much more than that. But that's exactly one of the surprises we had with why are they so rugged?
It's a vertical exaggeration.
They are still rugged. I can show you the distribution. They look more like a young mountain range. They have a lot more. Their tops have not been eroded. If you were to look at where when you erode a mountain range, you take the stuff off from the top. There's way more topography up high in those mountain ranges still. But you're right, it is exaggerated.
2 questions. On one of your final charts showing mass loss of the Antarctic glacier, it seemed to level off a little bit in the last decade or so.
Right.
Is that within the noise, or is there a reason for that to be real? Second question is, in the lakes, are there any signs of life?
Let's see, that we don't think that that's a slowdown permanently. There's no evidence that that's but we do think we have seen different these glaciers that come up, speed up and slow down. That's clearly a factor of how they change. So we think that that's some of the pulse that's going on. The life in the lakes, my kids, when we surveyed it, my son was convinced we were going to kill the dolphins that live there. I assured him we were not. The Russians at one point drilled a hole in to see if there was life there. We never heard back what they found because, well, no, their plan was to back pressure it and then drill back into back pressure it have the water come up and then sample the water that came up. Way more water that came up than they meant to, and I think the water was contaminated, so they were never able to conclusively say anything. There's probably microbes that live in the big lakes. In the ones in West Antarctica, they have drilled into those, and they're definitely microbes that live there. Because that was an ocean, probably 1 million or 2 years ago, and microbes happily live under those conditions. They live much deeper in the earth, so it's not that surprising. Dolphins would have been a surprise.
Are there any new technologies that you're excited about that will help explore in different ways than we can now?
Oh, I mean, I'm still excited about their places we haven't seen yet. I'm excited about the new technologies we can use actually to look at the change right now inside the ice sheet. There's a lot of work that goes on that maps the top, because that's easy to do from space. But I like looking inside and underneath, and I'm excited about some of the new ways by putting instruments on the top and letting them sit there, or the one you may have recently heard of where they put something down a borehole and listen. I'm excited about those because I often tell people who look at just the surface of the ice sheet, if you don't look inside, you aren't really going to know what's going on. It would be kind of like studying the ocean and claiming you knew all about the Gulf Stream without ever actually measuring the temperature profile and realizing it was only on the top of the ocean. So I'm excited about looking more inside in ways we can. There's one more in the front, and then well, I didn't show this picture, but the North Pole is an ocean, right? The North Pole, ice in the North Pole's maybe 5 to 10 meters thick, and it melts and moves. So you need very different technology to look at that. I mean, actually, Steve's been there. He's been on a ship. He's driven around a boat. You don't need an airplane like you do in Antarctica. So they're very different. I'd like to say Santa really would have a hard time because the ice moves a lot at the North Pole.
It wasn't a sailboat.
Over to you, Nate.
Okay. Well, thanks very much, Robin. Come on, that was really an awesome talk, wasn't it? And yeah, and I also want to thank everyone here for joining us this evening. Your presence is really especially meaningful this year now because we're celebrating Lamont's 75th birthday, and we're doing it all year. Lamont is one of the country's top Earth, ocean, and atmospheric research institutions. And throughout the decade, our mission has remained steadfast, and that is to deepen our understanding of the origin, evolution, and future of our natural world. And it's also one of the global centers of climate science, as Robin pointed out. And as Robin pointed out, our work is funded primarily through federal grants, and we squeeze out the value, all the value that we can out of every dollar. And everybody who works at Lamont knows that we do that. We get more out of each dollar than, I don't know, than I've ever seen any place. Okay, right now, as Robin noted, that funding is at risk. And in such times, support from individuals can make a big difference in our ability to perform our science-driven mission. And so as we navigate this moment in time, the support of individuals is critical for Lamont and our research community. So looking ahead, I encourage you to save the date for our next public lecture. It's on March 12th. It's Brendan Buckley. He'll share the fascinating stories of the research from Lamont's tree ring lab. And we look forward to welcoming you again, once again on our campus. And once again, remember that the support of individuals, particularly at this critical time, is really important for us. So thank you very much for coming.